start this lecture with a thought process from famous Albert Einstein. He says, "Only a life lived for others is a life worthwhile." It is a great statement. All of us must profess this in our life for knowing the efficacy of human life. If you recall that in the last lecture, we basically initiated discussion about the aerothermodynamics and its fundamentals, and in the very beginning we looked at what is a fluid flow and the way it can be classified. And we have just discussed little bit about various types of flows, namely steady and unsteady flow, laminar, turbulent flow, inviscid, viscous flow, and one dimensional, two dimensional and three dimensional flow, and also the compressible and incompressible flow. So, and later on we moved into the fundamentals of the thermodynamics, defining certain quantities like a system, and also we looked at three laws of thermodynamics that governs, and I was trying to relate the three elements of the thermodynamics with the life. And then we looked at the first law of thermodynamics, which says that whenever a system undergoes a cyclic change, however the complex the cycle may be, the cycle integral of work is proportional to cycle integral of the heat interaction. And we then derived the first law of thermodynamics for a closed system. If you recall, the closed system is one, there will be an energy interaction between the system and its surrounding, however, there will not be any mass interaction. In other words, the mass will be remaining same, although the boundary need not to be fixed, it may be vary like a piston cylinder system, where the piston will be moving in forward or backward direction or upward or downward direction, thus the system boundary will be changing. Today we will be looking at the control volume analysis. As I told earlier, the control volume is the one in which one has to concentrate or look at the changes occurring due to the interaction of system and surrounding. In case of control volume, there will be interaction of mass, because mass will be entering into the system boundary and also leaving sometime. And apart from this, there will be also the energy interaction to the work and heat. And if you look at rocket engines, can be analyzed very easily with a control volume, because the mass will be ejected through the nozzle for getting a thrust. And another common example which can be treated as a control mass is in a room in which there will be a fan which will be work interaction, you may heat the room, and then there will be heat interaction. If the doors and windows are closed and you are analyzing the heat interaction and work interaction inside a room, that itself is a control mass. But if the doors and windows are opened, then you can consider it as a control volume, because some of the fluids or air will be entering into the room and leaving the room. So, you can basically define the control volume as an arbitrary region in a space bounded by control surface through which mass also flows, apart from the energy in the form of heat and work. The control surface can be real or imaginary, it can be fixed and or movable. So, that is the control volume. So, let us look at a control volume which is shown here. In this case, the mass is entering into this control volume. Like if you look at, this is your basically control surface, it is having, which is corresponding to the boundary of this system, and entire is the control volume. There will be work interaction here because the fan is moving. There will be heat interactions because you are providing some heat. It can be electrical heat as shown here, or it can be also the solar heat or any other form of heat. The mass is entering into the inlet. This is, I can call it as a inlet, and it is leaving with the exit. And now this we will have to learn how to analyze the processes in this control volume system or a open system. This is also known as an open system. So, now for this, if you look at, we will have to take care of the mass balance, and that is very important for control volume. But in case of the closed system or a control mass system, the mass is not changing, therefore, it is already balanced. There is no need to take care of mass balance. In the case of control volume, you can see the rate of mass accumulation, this is the term, is basically rate of mass accumulation in control volume is equal to the mass is entering in the inlet. This is your inlet, and this is your outlet. We call it as exit outlet. That means mass is going out. That means whatever mass is coming in and mass will be going out, rest will be accumulated in the control volume, and this is known as basically mass balance equation, and we call it conservation of mass or mass conservation equation, balance, or I can say conservation equation, and we call it as also continuity equation in fluid mechanics. And that is, this analysis is a must in a control volume, unlike in a control mass system, it is not required. So, first law of thermodynamics for a control volume we are going to derive. Question arises how we can do that. We can do that by considering a control mass system in series. In other words, we will convert the entire process in a control volume in terms in series of a control mass system. In other words, by transferring the flow process in a control volume into series of imaginary non-flow processes in a control volume in succession. For example, if I consider the flow is taking place through a control volume at a certain time t, and then we will have to consider that as the system or a control mass system. For example, this is your control volume, and which is having heat interaction and work interactions, right. So, let us say that at initial state of time, certain amount of mass A is about to enter into this control volume through this surface, the entrance. Now, what we will do at this time, we will consider this as my control mass system. this as my control mass system, and then at the next time step, which is a small t plus dt, I will consider as my system as this portion of the mass which is about to leave this control volume. So, then my control mass system will be considering the control volume portion of this, including this mass B, this portion. That means, at time this is my control mass system or closed system, this portion red color. So, now keep in mind this delta t is very small, which is tending towards 0. So, that means what we are doing, the flow process in a control volume during the time dt, which is small, is converted into series of imaginary non-flow processes considering a closed system, and then we can apply the equation for the control mass system what we had derived in the last lecture pertaining to the first law of thermodynamics, or that is basically energy balance. Then we can derive it, and you can do that, but I am just writing down here the final expression, which is basically rate of change of energy. This is rate of change of energy, and this is your the total amount of energy. This portion is the energy, total energy leaving exit of CV, and this consists of the enthalpy. Of course, this is the mass flow rate at the exit, and this is your kinetic energy. This portion is kinetic energy, and this is your potential energy. And similarly, this is the total energy which is entering, total energy entering into CV, and this is your heat interactions, heat flow rate, and this is your work done on the system. And keep in mind this enthalpy is consist of two terms, one is U plus PV. U is your internal energy and PV is your flow work. And if you can think, this flow work makes the fluid to enter into this control volume, and that is the pumping work one can think of. That means, this is the pressure which will be acting into this fluid to move into the control volume. Now, this is the first law of thermodynamics for control volume, and which you can use for analyzing an open system or a control volume system. So, we will now look at Clausius inequality, which is one form of the second law of thermodynamics. We state that whenever a system undergoes a cyclic change, however complex the cycle may be, the algebraic sum of all the heat interactions divided by the respective absolute temperature at which heat interaction takes place considered for the entire cycle is less than or equal to 0, and that is basically the Clausius inequality, and mathematically it can be expressed as the cycle integral of dq divided by t is less than equal to 0, and this is the amount of heat which will be interacting with respect to certain temperature, reservoir, or it may be sink, whatever it may be, depending on that it has to be looked at it. And this is of course for a cyclic process. However, for a closed system it will be different, as we had seen. For a closed system, that is equal to change in entropy. This is S is your entropy. Change in entropy is greater than equal to dq by t, and for reversible process the change in entropy is equal to dq by t, whereas for an irreversible process change in entropy is always greater than dq by t, because of fact that there will be lot of frictions and other non-reversible processes will be there, which you cannot really do. Most of the processes are irreversible in nature. And second law of thermodynamics for an open system we will be considering now, and we will be considering the same control volume having the work interaction and then heat interactions, and this is your inlet through which mass will be entering, and this is your exit through which mass will be leaving out of this control volume. So, you can derive this expression. I am just putting the final form, that is states that change in entropy with respect to time is equal to the total entropy, which is consist of the entropy which is entering and the generated due to the heat interaction, that is dq by t, minus the amount of entropy which is leaving the control volume through its exit, plus the Sg. Sg is the entropy generation and rate, and dq, as I told, is basically heat transfer during the time dt, which will be taking place in this process. So, now armed with these equations, which will be will be analyzing the problems related to the rocket engines. But now we will have to look at the governing equations for fluid dynamics. For the fluid dynamics, we need to make some assumption which we have already stated, particularly the continuum flow, and where the fluids are elements are very closer to each other, unlike in the space where the mean free path is quite large. That means during between the distance traveled between two consecutive collision, what we call it as a mean free path, is quite large, provided the pressure is low, as in case of space where one can look at a rarefied gas, but in our case we will be using the continuum flow, and we will be dealing with Newtonian fluid, where the shear stress is proportional to change in velocity, and which we will be doing, as most of the fluid will be Newtonian nature, and when we are dealing with the rocket engines, we will restrict ourselves to the single phase and perfect gases. However, in rocket engine we need to look at also the two phase flows and even sometimes three phase flow, and we will be discussing whenever it will be required. It is not only will be restricting to the single phase. Right now we will be restricting our discussion to the single phase only, and generally we will be ignoring the body forces. Body forces can be anything. It can be electrical, it can be electromagnetic forces, electrostatic forces, it can be gravitational forces, but which will be not considering. But and in this fluid flow our objective is basically to look at the unknown quantities like the density, velocity. Velocity can be in all three directions, x, y and z. As I told earlier, we will be dealing with mostly the one dimensional flow, and pressure is the driving force for the fluid to make it to move, and so also the temperature which we will be dealing with, and all these properties are very important for analyzing the aerothermodynamic aspect of the rocket engine. So, when we are talking about the aerodynamics, then we will be basically looking at the conservation of mass, as I told earlier. This is also known as continuity equation. Conservation of momentum, that we will have to ensure. Navier-Stokes equation, that is known as, and the conservation of energy, the energy equation, which we have already discussed in thermodynamics. And beside this, we will have to look at also the equation of state, as we will be dealing with mostly the compressible flow, but whenever we are looking at liquid, then we will be looking at incompressible flow, particularly atomization of the liquid fuel and other things. So, all these problems pertaining to the aerodynamics or fluid dynamics can be analyzing by considering all these equations. So, therefore, we will be getting familiarized, rather recall these equations in a very succinct manner, because already you have learned about it. Just we will try to make you to recall. So, basic principle of fluid dynamics, if you look at governing equations of the fluid flow, whatever we have looked at, that is the continuity equation or the mass conservation equation. We have already seen the rate of accumulation of mass, this term rate of mass accumulation in CV, control volume, is equal to the mass is entering into the control volume minus the mass is going out from the control volume, and that is the differential form of the mass conservation equation. And we will be looking at something about the integral form of this equation. Let us consider arbitrarily a control volume. This is your control volume with the control surface. This is your control surface. The streamlines are moving through this, and let us say there is a fluid element is having some area, and this which is having, this is your normal vectors, and it is moving with certain velocity, making angle theta with the normal vector. Now, when you talk about this elemental mass flow rate would be basically change in the mass flow rate in this element is equal to rho v. V is the velocity. This means this is bar basically magnitude of velocity, cos theta into dA. Cos theta will be along with this direction, that is on the normal. So, we can write down that basically as the mass within this control volume will be m C V rho into d V. This is basically the d V is the volume of the fluid element, and by using the above expression, integral form of continuity equation can be derived as rate of change of this mass in the control volume into the rho v dot n dA, and this is nothing but your rho v dot n dA you can look at. So, that is basically the integral form of continuity equation, and above expression can be obtained directly from the differential equation, that is 1 by using the Reynolds transport theorem, and which all of you will be familiar with. So, that you can derive, but what it says, it basically says very simple one, that the rate of mass of accumulation, right, in this control volume will be plus the amount of mass flux. This is basically is the mass flux through CV control volume is equal to 0, that it says. So, therefore, this is basically about the mass being conserved, and this is also known as the mass conservation equation, and this is the integral form which is easier to use, and we will be using this, and sometimes we will be using also the differential form of the equation. So, we have already talked about this thing which is very important, mass conservations, and in the next lecture we will be discussing about the momentum conservation equations, and later on we will be looking at basically the little one dimensional steady flows and how to handle that, and including little bit certain definition pertaining to the compressible flow as well. Thank you very much.